So our next speaker is Gonzalo Rada. Gonzalo Rada is Principal Payment Engineer with Wood, where he has worked for 29 years and is an expert in payment design, evaluation, maintenance, and materials. He is active in ASTM, ASCE, and TRB, where he chairs the Committee on Payment Structural Evaluation and Modeling. His research has included many projects for the Long-Term Payment Performance Program in FHWA and NCHRP.
And a very good morning or probably afternoon for a lot of you. I'm delighted to be a part of this session and really do appreciate the opportunity to give this presentation on the impacts of preservation treatments on payment performance. Most of the presentation is based on work that was done under NCHRP Project 1433 and to a lesser degree on NCHRP Project 1438. Both will be covered, but before doing so, I do want to acknowledge the remaining members of the research team, starting with James Bryce, now with Marshall University in West Virginia, Gary Higgs and Ding Cheng with Chico State University in California, Beth Vicentin with the City of Raleigh, North Carolina, Mike Heitzman, now retired from NCAT, and last but certainly not least, Amir Hanna, who served as the NCHRP Senior Program Officer on both projects. Now, I'm going to start this presentation by providing a bit of background information on the effects of preservation. I will then move on to the two NCHRP projects with particular focus on the development of models to quantify the effects of preservation. And this is where we'll spend the bulk of the time. And ultimately, I'll conclude the presentation by highlighting some of the key findings from the two NCHRP projects. So moving on to the background information. For purposes of both NCHRP projects, payment preservation was defined as a set of activities intended to maintain or to improve the functional condition of payments at a relatively low cost and while the payment is still in relatively good condition. Now, this figure illustrates the possible effects of preservation using a performance measure that increases with worsening condition. So the x-axis represents payment age, the y-axis represents payment condition, going from very good at the bottom to very poor at the top. The dashed line here represents the performance of a payment that does not receive application of preservation. And the solid line here, purple, is the performance curve for the same payment as this one, but this one has received the application of a treatment. So with this figure, the first effect illustrated here is the immediate change in condition, or this vertical line that drops from the dashed line to the x-axis. So for example, application of a thin asphalt concrete overlay will significantly reduce or eliminate rotting, as could be the example here. Another treatment, however, such as chip seal, is unlikely to have much of an effect on rotting. Now, the second effect is the impact on the performance or the change of condition over time, or the performance of the payment over time. And that's illustrated here by this shaded area. So in essence, this is the improved performance, the benefit from the preservation treatment between without and with preservation. Now, in this figure, a threshold condition is shown here by this red horizontal line. It's basically represent the point beyond which preservation is no longer considered viable. It also helps illustrate the concept of service life extension. In other words, when a treatment is applied, how much longer does the payment last before reaching that critical condition? This slide further illustrates the effects of preservation on payment performance, but this time we're looking at a performance measure that decreases with worsening condition, as would be the case payment condition index as an example. Now again, the x-axis on both figures represents payment age, y-axis payment condition, but now going from very good at the top to very poor at the bottom. The dashed line is the performance of the payment without preservation, whereas the solid line represents the performance with the application of a preservation treatment. So if you look at the figure on the left, you'll notice that in year 5, a treatment is applied and there's an immediate improvement in the condition of the payment. But after that, the deterioration or the distress growth rate pretty much remains the same as prior to the treatment. The figure on the right, on the other hand, shows that the treatment applied in year 5 has no immediate impact on the condition of the payment. However, over the long term, it reduces the deterioration rate or the distress growth rate of the payment. So with this in mind, and moving on to the first of the NCHRP projects, the objective of 1433 was to identify or to develop performance measures that consider the contributions of preservation to payment performance, service life extension, and life cycle costs. Now, assuming that objective was achieved, then the second objective was to prepare a set of guidelines for implementation of the recommended measures by highway agencies. The project started with an information gathering effort that included both a literature review and a survey of highway agencies. The objective of the literature review was to identify as many potential performance measures as possible. Ultimately, at the time, more than 40 measures were identified, and they were grouped into the 4 general categories shown here. Individual distress or condition, that could be IRI, cracking, rutting, and faulting. Composite payment measures could be or included payment condition index, payment quality index, payment condition rating, and so on. Cost-based measures, examples, equivalent uniform annual cost, or the equivalent single axle load efficiency factor. And the 4th category pretty much included everything else, whether it was noise, risk, asset sustainability index, or remaining service interval. Moving on to the survey of highway agencies, the objective here was to assess the use of preservation by the highway agencies, and as shown on this slide, 33 of the 50 US states responded to the survey. Similarly, 9 of the 13 Canadian province and territory highway agencies responded. So we had an overall response rate of 67, which was pretty good. More important, the survey provided valuable information that we used in the follow-on activities. If you look at the figure or the plot at the top, for example, what we found was that for asphalt concrete pavements, the top 3 treatments were thin overlays, chip seals, and microsurfacing. And if you look at the slide, the plot on the bottom, you'll see that diamond grinding, partial deep depth patching, and joint sealing were the more common treatments. Now, keep in mind, this is about 3-4 years ago. Going back for a second to the literature review, again, I noted that more than 40 measures were identified. Those measures were evaluated using various criteria, and I'll touch on some of it in just a second. But ultimately, we ended up recommending the 4 measures that are listed here: IRI, cracking, rutting, and faulting. And there were many reasons for this, but I'd say that the primary ones were, first, most agencies use them in their payment management activities, and so they are familiar with them. Also, agencies are required to submit them to the Federal Highway Administration as part of the HPMS data submittals, and therefore these data elements are most likely available. They also include the stresses that typically trigger preservation treatments. And very important in terms of the project is the fact that these measures capture the effects of preservation on payment performance, as I'll demonstrate starting with the next slide. Now, to validate the 4 performance measures that were listed in the previous slide, we gathered data from 8 state DOTs. 6 of them provided asphalt concrete preservation treatment information. The other 2 provided information on Portland cement concrete preservation treatments. We also used a good deal of information from the long-term payment performance or the LTPP database. Now, as you may recall from the start of the preservation, there are 2 effects that we're trying to model in terms of quantifying the effects of preservation. One of them is this immediate change in condition after application of the treatment. And the second one is the benefit in performance, the change in performance over the long term resulting from the treatment. So the data from the 8 state DOTs as well as the LTPP program were used to develop models to quantify both of these effects. Now, starting with immediate change, this plot on the left shows the stress as a function of time. This first point happens to be the condition of the pavement prior to application of the preservation treatment. This point over here is the condition of the pavement immediately following the application of the preservation treatment. And the difference between those 2 is that immediate change in condition. In this case, it happens to be, again, a performance measures that increases with worsening conditions. Now, we did this, we estimated this immediate change for every pavement segment within each combination of performance measure and preservation treatment. And we use that to generate relations such as the one that you're looking at here on the right. So basically, x-axis is a condition of the pavement prior to the treatment. This is a change in condition as a result of the treatment. And in this particular case, the relation shows basically that the worse the condition prior to treatment, the greater the improvement. And that was a very common finding, but we also had the case where it didn't matter what the condition was. It was pretty much, it pretty much remained the same. So you, in essence, you had a horizontal curve. So to show you real life data, here you are looking at the immediate change in IRI resulting from the application of a thin asphalt concrete overlay. You're looking at data from the LTPP program at the top, Virginia DOT in the middle, and the Ohio DOT at the bottom. So basically the x-axis, which is the condition before the overlay. If we take Virginia, condition is 150 after application. It would be reduced by approximately 60. So the resulting IRI after the thin overlay would be somewhere around 90 points. Now, this, going to the higher data for a second, there are 2 regressions. This one, which is almost flat, and the green one. The one with the dashed line includes this point that we found to be an outlier. So very important to be careful how those outliers are handled, because you can get an immediate response model that's not quite accurate. If that point is removed, then the model that we get is again shown in the green line. And if you compare this one to the one from Virginia, you'll notice that the coefficients are almost the same, 0.53, 56, 33, 37. So quite good. And if in addition you look at the LTPP data, then you'll notice that it's not the same, but the trend is very similar between the 2. Here is another example of immediate change, but now looking at the impact of diamond grinding on faulting. X-axis represents faulting prior to the grinding. Y-axis represents the change in faulting as a result of the grinding. And basically what you can see from the regression equation is that faulting is reduced by about half after diamond grinding. So if faulting is around 0.2 prior to grinding, after grinding it is reduced to half, or to about 0.1 inches. Now, this plot was generated using data from the LTPP program. I meant to include data from Washington State, and that one was even more dramatic in the sense that faulting improved by 80%, 85%, so more significant. Okay, so now moving on to the long-term changes in performance, it would have been great if we had a control or an untreated section, with every section receiving, or every segment receiving a treatment, but that was not the case except for a group of LTPP data. So as a result, we defaulted to looking at the deterioration, or at the distress growth rate, as the means of assessing future performance. So if you look at these three plots on the left, basically what you have is change in condition versus time for three segments. Time 0 represents the time when the treatment was applied. So for each segment, we basically ran a linear regression line through the data to calculate the slope, which represents the distress growth rate. So we did this for every single segment, for every within each combination of performance measure and preservation treatment. And the resulting data were used to generate relations such as the one illustrated here. Again, growth rate as a function of condition prior to treatment. That was one of the things that we looked at, but as you'll see shortly, we also looked at the effect of climate, the effect of traffic on the growth rates. Okay. In this figure, what you're looking at is the rod growth rate in inches per year for LTPP test sections that were treated with a thin overlay. And it is compared to the growth rate of untreated. So it's basically treated test sections versus untreated test sections. No, it's not perfect, and perhaps it's a little difficult to see, but what we found was that the growth rate of the control test sections tended to be higher than for the treated test sections. We did carry out statistical tests to determine if the performance between the two were similar or not, and they were confirmed to be similar. Now, in this figure, it also shows the effect of a thin overlay on the rotting performance. Here we're looking at Virginia DOT data. But in this case, the rod growth rate in the y-axis is shown as a function of the pre-overlay rotting. In other words, the rotting prior to treatment. Now, as you can see from the slope of the regression line, it's positive, meaning the higher the rotting prior to application of the overlay, the higher the rod growth rate. Now, as I mentioned earlier, we also explored the development of rotting performance models for sections treated with a thin overlay. Well, let me rephrase that. What you're looking at here is the comparison of predicted rod growth rate in the x-axis versus the actual growth rate. Excuse me for 1 second, please. versus the actual rot growth rate on the y-axis. Now, treated test sections are shown by the small open circles. Control test sections are shown by the red plus signs. And the predicted values we're generating using models that contain the variables listed here on the left. 3 of them are climatic factors. 1 is payment structure, and the other traffic. So in essence, the factors that affect the performance of a payment. Now, as you can see from the R-square values as well as the p-values, the ROT performance for both treated and controlled test sections can be predicted quite well. Now, the focus so far has been on NCHRP project 1433, so I'm going to move on to NCHRP project 1438 and spend just a few minutes on that project. The objective of this project was to develop a guide for the timing of asphalt surface pavement preservation, taking into consideration condition and non-condition factors. Condition would include any of the 4 performance measures that I've been referring to. Non-condition factors include preservation, treatment type, pavement structure, subgrade soil, traffic, and climate. Again, the factors that affect the performance of pavement. Now, as I'm sure all of you know all too well, the timing of preservation treatments is a question of when benefits are maximized and costs are minimized. The majority of preservation timing approaches suggested in the literature are based on cost-benefit analysis, where the differences in the definitions of benefits and costs can vary. But in every case, benefits are defined in terms of the change in performance or service life resulting from the treatment. Now, that being the case, it's also important to recognize that those factors that affect payment performance also affect the timing of preservation, whether they are condition or non-condition related factors. So the point being that the effect of treatments on payment performance is at the heart of the timing issue. Now, in the development of the new models for 1438, data from 10 state DOTs was used. 8 of these were the same DOTs that provided data for NCHRP project 1433. Those same state provided those data plus an additional 1 or 2 years of performance data. Then we also had Tennessee and Maine provide data in support of the project. You'll notice that in a couple of cases, Kansas and Ohio, we basically got access to the entire database, which was great. Please also note that in some cases, let's say Virginia, we got information on thin overlays and chip seals, but not microsurfacing or slurry. Oh, let me go back here. So important to show, to point out that in most cases, except for perhaps Utah, we had 10 or more years of performance of condition data, and that was extremely useful. This slide points out that most agencies do not store climate or subgrade soil data in their payment management databases. So in the project in 1438, we in essence developed default data sets at the county level for use in the preservation models. Now, county level is pretty coarse. Since this project, we've gone much more refined scale than the county. So in any case, using the data from the state DOTs and from the LTPP program, models were developed for the most common treatments and for the recommended measures, both of those based on NCHRP projects. So the treatments, again, this project was only asphalt concrete preservation, so thin overlays, chip seals, microsurfacing, and slurry seal. And the performance measures were IRI, rotting, and cracking. This figure that you're looking at now shows the effect of a thin overlay on rotting, and this is based on data from both the Virginia and the Ohio DOTs, as well as the LTPP data. The x-axis is the rotting prior to application of the overlay. The y-axis represents the reduction in rotting due to the overlay. The dashed line represents the maximum possible improvement. So for example, if the rod is 0.3 inches, that means that the maximum possible improvement is 0.3 inches. The blue line here is the actual regression line through the data. And please note that it doesn't matter what the rotting before the overlay is. The resulting rotting after the overlay is, well, what we found is that it was 0.1 inches based on the available data. So if it's 0.2 inches of rotting prior to treatment after the thin overlay, the improvement is 0.1, so it would be reduced to 0.1. Same thing here. If it's 0.5, it's a 4.4 inch reduction, which again would take it to 0.1 inches. Now, this figure addresses the effect of chip seals on the performance of pavement in terms of IRI. We found that chip seals have no immediate effect on IRI, but they do affect the IRI growth rate. Now, using the available data that I summarized a minute or so ago, we explored all sorts of models, and we found that the best one was one that included the variables that you're looking at here. Mean annual freeze-thaw cycles, mean annual air temperature, subgrade modulus, mean annual precipitation, and average annual daily traffic. Also IRI before treatment in terms of the condition variables. Now, I've arranged these variables according to the sensitivity of the model to the variable, with the more sensitive ones at the top. Again, as you can see, the best model is a function of the condition before treatment, as well as the non-condition factors listed here. And if you look at predicted versus the predicted values represented here by the y-axis, if you look at the predicted versus the measured values used in the model that was developed, it's certainly not perfect, but we feel pretty good. I inserted this slide here because it's ultimately where we want to arrive in terms of quantifying the effects of preservation. The curve at the top represents the pavement section without the application of treatment. If that pavement receives a thin overlay, you'll notice first the immediate change in condition. You'll also notice that the IRI growth rate significantly flattens in comparison to the pavement without treatment. So, and if we're able to do this, in other words, quantify both the immediate and the longer term effect of preservation, then we can start addressing all sorts of project level, network level, strategic level necessities by highway agencies. So to conclude the presentation, NCHRP Project 1433 was completed a few years back, and it resulted in a report number 858, published in 2018. Included in that report is guidelines that help in the selection of performance measures. We recommended 4, but agencies can, of course, select other performance measure. The guideline also provides information, instructions on how to go about developing these immediate and long-term effect models. Now, another couple of very important findings from both projects were, number one, there's so much data available to highway agencies that it's important that those agencies start using those data to develop their own model to quantify the effects of preservation. Sort of related to that is the fact that analysis techniques that perhaps as pavement engineers we've not used often, but there's so much good stuff out there that it should certainly be considered and brought into the modeling of the effects of preservation treatments. Well, finally, the models developed in NCHRP 1435 to quantify the effects of preservation can be used as a starting point as default models, but ultimately going back to the first and second point, it's important that agencies develop their own models. And with that, Adriana, I will turn the presentation back over to you. Thank you.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.